Hello dear students, welcome to Pen and Paper Chemistry on YouTube. This is a very lengthy topic, but it is very important that we do it in one go. So I would request you all to take short breaks between different properties, but stay connected. Promise by the end of this video you will be very comfortable with the topic of periodic table and periodic properties. To understand the periodic properties in the best way, please make sure that you have a periodic table by your side, either a hand-drawn one with the electronic configuration written for the elements, or a printed periodic table from any of your textbooks will also serve the purpose. Our topic is periodic properties. That is what we are going to do now. After we have already spoken about periodic table and how to draw the periodic table, we need to first understand what do we mean by periodicity. Although this is something which you have been observing it ever since you entered school. So you have a 40 minutes class 1, first period, second period, third period, each ranging from for 40 minutes, 30 minutes, 35 minutes. So what is happening is it is repeating itself. The classes are repeating themselves after regular intervals. That is what we call as periodicity. Something which repeats, or there is a regular pattern to it at regular intervals of time is what we call as periodicity. If you remember, we have spoken about Mendeleev, how Mendeleev felt that the periodicity of elements could be explained on the basis of their mass number. But this was later on proved to be wrong, and Moseley said no, not according to the mass number. Periodicity varies with the atomic number of the elements, and this is what we are going to study today. So let us start with the first periodic property, atomic size. Now before I explain you the atomic size, let us recall a few points that we have studied in the periodic table. Periodic table divided into horizontal rows, vertical columns, horizontal rows called periods, vertical columns called groups, 18 groups, 7 periods, right? This is simple recall of what we've already done. Let us see nuclear charge. Nuclear charge means, what does nuclear charge mean? Nuclear charge comes from the protons. Yes, and protons are equal to the atomic number of the element. So if you see in any period, atomic number 1, 2, 3, 4, 5, 6, 7 and so on and so forth. So what is happening when you are going along a period or across the period? How is the atomic number varying? Just like the variation of the atomic number, there will be the similar variation in the nuclear charge, because nuclear charge is same as atomic number. So across the period, the atomic number increases by 1, and so does the nuclear charge. Now this ATP does not stand for adenosine triphosphate. Yes, I'm sure you must be getting confused. These are short forms that I have devised so that my teaching and as well as understanding of the topic becomes a bit easier. Just adjust to this, okay? ATP, now these are not standard symbols, okay? This is for just this class. Please don't use them in your examinations. In the exams, you have to mention down the group DTG, across the period ATP. It's just to make it simpler. So nuclear charge, across the period it is increasing by 1. What is happening down the group? What is happening to the nuclear charge? Yes, there also it is increasing, but what is happening is here, let us suppose we take the case of helium and neon. The nuclear charge increases by 8, right? Let us talk about neon and argon. The nuclear charge again changes by 8. Argon and krypton, the nuclear charge increases by 18, and so on. So what is happening is the nuclear charge, the positive charge on the nucleus is increasing as we are going down any particular group as well. Next property, valence shell, the outermost shell. Come to the first period, the outermost shell is the first one. Of course, that's the only shell which is filled up. So you have 1s1, 1s2, 2s1, 2s2, 2s2, 2p1, 2p2, 3, 4, 5, 6, right? Please keep your periodic table which you have drawn handy so that you are able to understand. Also, earnest request, please keep a pen and paper handy so you can write down points for yourself, and your notes are also ready by the end of this class, right? So what is happening? The valence shell here, lithium, beryllium, boron, carbon, the valence shell is 2 in all of them. Valence shell is 3 in all of them. Valence shell is 4 in the 4th period, 5 in the 5th period, 6 in the 6th period. So what is happening to the valence shell when you are going across the period? Yes, you got it right. It remains the same, right? Let's check about down the group. Go on. See the electronic configurations that you have written. If you've drawn a full periodic table, now you'll be able to relate to it and you'll find it very handy. So it's 1s1, 2s1, 3s1, 4s1. So what is happening to the valence shell as you're going down the group? Yes, it is increasing by 1. So when you have, obviously you have in a particular group, the period number is increasing, yes, and that relates to the valence shell. Now I'm going to talk about shielding effect. Now I have made a separate video on shielding effect under the topic atomic structure, but just to touch base. Shielding effect. Now let's suppose we have a teacher in the class, right? Now these are my front benchers, second row, third row, fourth row. Now who gets the most attention according to you in the class? Yes, the first row, then the second, then the third, and usually the last benchers get ignored, right? There is a lot of students that the teacher has to pass through in order to pay attention to the last benchers, correct? So the similar scenario is observed in the case of an atom. Now I am not drawing the 3D model nor the quantum mechanical model. I am just explaining you by a simple example over here where I have got the nucleus. The nucleus has the protons. The electrons are present at certain distances. Now how would be the force of attraction between the, so if let's suppose the force of attraction between the nucleus and the electron in the first orbit is given, let's say 10. What would be the force of attraction between the nucleus and an electron in the second orbit? Less than 10, more than 10? Yes, it will be less than 10 for an electron in the second orbit. What would be the force of attraction of the proton for an electron in the third orbit? Yes, even less than how it is for the second orbit. Why? Because the electrons which are there in between, they are vying for attention and attraction. They say, this proton belongs to us, this attraction belongs to us. How can it spread further? Right? So they tend to concentrate the attraction to themselves. So what happens is with every step, that force of attraction actually decreases. Right? This is what we called as shielding effect. The inner electrons, they shield the protons from spreading their attraction or pulling the electrons of the outermost shell towards themselves. Correct? So across the period, what is going to happen? Now when you see across the period, although we cannot give very strong, see here in the case of the S and the P block, the electrons are being added only to the valence shell, whereas the number of electrons in the inner shell is remaining the same. So the shielding effect is remaining almost constant, although the nuclear charge is increasing. On the other hand, in the case of D block, because the electrons are being added to the inner shell, as well as the F block where they are being added to the antipenultimate shell, what is happening is the shielding effect is much more. So keep this in mind when we are going to talk about the next property, that is the atomic size. Mind you, what we are going to do over here are simple generalizations. There are exceptions. So when you do the S block, the P block separately, and when you will be talking about each group separately, you will find minor variations. But if your basics are in place, I'm sure you will be able to explain why those variations are there. I will take a few basic examples in this video itself. Come to our first periodic property, the atomic size. That means the size of an atom, as the name indicates. It is also called as atomic radius. How do you define radius? This is a circle, the distance of the circumference from, or the distance of the boundary from the center of the circle. This is what we call as radius. This atomic radius can be defined in many different ways. So you have the radius when two atoms have undergone covalent bonding. Now mind you, to determine atomic radius of an individual element or an individual atom is very difficult, because the size of the atom is very small in terms of angstrom units, that is 10 to the power minus 10 meters. Now that's very small to be measured. So we have to rely on derived data. First, covalent radius. Very simple. You have two atoms which are covalently bonded with each other. You take the distance of their nuclei, halve it, and this half is what we call as the covalent radius of the atoms, of the similar atoms which have undergone covalent bonding. Very simple example, chlorine, Cl2, chlorine atom, covalently bonded to each other. So the distance between their nuclei, it is, if you halve this distance and half of the internuclear distance between two covalently bonded atoms is what gives us the covalent radii, right? Next, you can also define ionic radii. What is an ionic radii? The radius of the outermost shell from the nucleus in an ion will give me ionic radii. What will be metallic radius? Now for that you need to know metallic bonding. If you know metallic bonding, you can define metallic radius also. All these points I shall also include in the write-up so that it's easier for you to remember and touch base when you have your examinations. So how do you say in the case of metallic bonding? There is a metal positive kernel which is surrounded by a sea of electrons, right? So the distance between their nucleus divided by 2 gives me the metallic radius, right? All of these will be in angstrom units. Here, let's talk about in general, right? How will the atomic radius vary? when I am talking about across any period and down any group. Please don't forget about the nuclear charge, the valence shell, right? Let's say I'm taking one period, I'll take n is equals to 3. So I'm taking about the third period. Here what is happening is, the nuclear charge is increasing, yes. The number of valence electrons is increasing, yes. The number of valence shell is increasing, no. The electron at each point of time is getting added to the third energy level only, right? So with the result, there's these protons trying to pull the electrons towards themselves, them. Now, the number of protons is increasing, the number of electrons is increasing, yes, but at the same distance at every point. So what will happen to the size of the atom as you go across the period? Remember, the electron is not going into a new period. It is not going into a new valence shell. So what do we have over here is, I've got the nucleus 2 and 3, right? So here there was an electron, first one, sodium. In the case of magnesium, there are 2 electrons. Now there's a pull of the protons for the electrons, correct? And at each stage also remember the number of protons is also increasing. So if I have aluminium, there are 13 protons pulling 13 electrons, and out of these 3 electrons are in the third shell only. Silicon, 14 protons, 14 electrons, and in the third shell itself, right? Because its configuration is 3s2, 3p2. So what happens? They are not letting them move away. So what is the force of attraction? It is increasing. So what will happen to the size of the atom? Now there are these the protons which are pulling the electrons, you know. If the electrons are increasing, the protons are also increasing in number, and there's this tug of war. So what is happening? See, 1 pulling 1, 2 pulling 2, 3 pulling 3, 4 pulling 4. So what is happening? That is becoming stronger. So with the result, the atomic size across the period will, yes, it decreases. Once you understand this concept, the other 3 properties are smooth sailing, not a problem at all. Let's talk about down the group. Let me take group number 16. So I have 2p4, 3p4, 4p4, 5p4, 6p4, 7p4. So what is happening? The number of valence electrons, yes, the valence shell, the number of valence electrons is remaining the same. But what is happening to the number of valence electrons? Yes, the number of valence electrons is remaining the same. The number of valence shell is increasing by 1. I'm glad that you are paying attention. Correct. Oxygen, sulfur, selenium. So you have over here 2p4, 3p4, 4p4, 5p4 and so on. So what is happening here? The number of valence shell is increasing by 1. The number of valence electrons is remaining the same. So in the first case, I have this situation. So there are 4 electrons here. There are protons in the nucleus. Second case, what is happening is, again nucleus, again 1, 2, but the 4 electrons are now in the third orbit. The valence electrons are in the third orbit. So what will happen? So although the number of protons has increased, but what will happen because of the addition of an extra shell? What will happen to the size? So it is like if you have a class, you have 10 new students joining the class, right? So you will have to put an additional row at the back in order to accommodate those 10 students. So what will happen? The size will increase. So down the group, what is the generalization that we can give about the atomic radius? Down the group, atomic radius, yes, it increases, because although the nuclear charge increases, the number of valence shell is increasing and the shielding effect will also increase, because what is happening is there are electrons which are coming in the inner shells. I hope till this point it is clear. If it is not, just pause the video, explain to yourself, go through the video again if you are not clear, and then try to understand and get ready for the next property. Seriously, if you have not understood, don't carry on, just pause, think for yourself. Also notice over here that the noble gases, they have exceptionally high atomic radius. Can you think of a reason why? Yes, because they have a completely filled, yes, valence orbital. Correct, because it is 2s2, 2p6, 3p6, 4p6 and so on. So all their electrons are paired up, they are relaxed, they are chilled, right? So they are not bothered. So compared to the others, their atomic radius is slightly more, right? Next, get ready for ionization enthalpy. Ionization enthalpy, also called ionization energy, also called ionization potential. Now, if you understand the meaning of the term ionize, then ionization enthalpy or ionization potential will be very easy for you to understand. Ionization means when you remove an electron from an atom. Simple. You have ionized it, you have converted it into an ion. Yes, I agree. Ionization can also be when you convert an atom into a negative ion, that is an anion. But in this case, we are specifically talking about ionization enthalpy or ionization energy in terms of loss of electron. Now, when we will define it, we will say when the amount of energy required to remove an electron from a neutral gaseous atom. Or okay, let me add one more thing over here. The amount of energy required to remove the most loosely bound electron. This loosely bound is usually the valence electron. The amount of energy required to remove the most loosely bound electron from a neutral gaseous atom, right? All these words are very, very important when you are defining it in the true sense of the word ionization enthalpy. Now, if you see over here, I have used the word enthalpy. If you have not done thermodynamics, which for a beginner usually you will not be able to understand, this is a thermodynamic term and we represent it as delta Hi, and this has a positive value. Why a positive value? Because you have to give it energy. Energy has to be given to that atom in order to extract electron out of it. So anything that is given to the system is positive, taken out is negative. So because you are removing an electron by giving energy, that's why it's a positive value. You will find it written as kilojoule per mole, or in some places as kilojoule per atom as well, also as electron volt per atom. So don't get confused. because these are all terms related to energy. Yes? So when you remove an electron from a neutral gaseous atom, you get an ion, and the energy involved is called as ionization energy or ionization enthalpy. What if you remove 2 electrons? Yes, again that can also be ionization enthalpy, right? So what will you call that ionization enthalpy as? Yes, it's called as the second ionization enthalpy, because in that case it will result in a 2 positive charge and an electron is being removed from an ion over here in the gaseous state. The ionization energy here will be called as IE2, and that is second ionization energy. Same way you can have third ionization energy, and so on and so forth. Although you usually do not remove more than 3 electrons, that you would have done in chemical bonding as well. So how does the ionization energy or ionization enthalpy vary in the periodic table? Do we have a periodicity in the ionization enthalpy or not? Let us see. And also there, I have told you earlier also, there are anomalies. We shall deal with them as we come across during our study of the S and the P block. Ionization enthalpy. Now you want to remove. What is easier to remove? Something which is loosely bound to the electron or something which is tightly bound to the electron? Yes, something which is loosely bound, correct? So if you have a loosely bound electron, will your ionization enthalpy be high or low? Think and tell me. Will you need a high amount of energy or will you need less amount of energy? Yes, you will need low amount of energy in order to remove an electron which is less strongly bound compared to an electron which is strongly bound. Okay. Second question. Is it easier to remove an electron from a bigger atom or from a smaller atom? Yes, from a bigger atom, simply because the electron will be less strongly bound. Correct? Now, let's do any particular period. Again, let's see third period. When you're talking about the third period, what is happening to the atomic size? As I said, once you've understood the atomic size, then everything is easy. Moving across a period, the valence shell remains the same. Number of valence electrons increases. The nuclear charge increases. What is happening to the size of the atom? Think before answering. Yes, it is becoming smaller. When it is becoming smaller, will it be easier for you to remove the electron or will it be difficult for you to remove the electron? It's smaller. Smaller means more compact. More compact means closely attached to the nucleus, the protons, strongly bound by the nucleus. Yes. So what will happen is across the period, the ionization enthalpy will actually increase because the atomic size is decreasing. Right? Does that make sense? Come to down the group. When you are talking about down the group, here, what is happening to the atomic size? Here at each stage, if you notice, the valence shell is increasing. The number of valence electrons is remaining the same, but second, third, fourth, fifth, sixth, what's happening to the size of the atom? Yes, it is increasing. Will it be easy or difficult for you to remove the electron? Very easy. So down the group, ionization enthalpy will increase or decrease? Yes, it will decrease. What can you tell me about the noble gases? Will they have high ionization enthalpy or low ionization enthalpy? Think and tell me. Group 18, will it have high or low ionization enthalpy? Yes, it will be very high because of their stable configuration. All their electrons are paired up. So what will happen? There they will need a very high amount of energy to remove the electron from them, because all their electrons are equally bound. There is no loosely bound electron. That is why their ionization potential is very high. Okay, let's compare something else also. You have magnesium and you have aluminium. Now I am saying that across the period in general ionization enthalpy should increase, right? That's what we said just now. Across the period it increases. What has been observed is that if you go from magnesium to aluminium, see, ionization enthalpy should increase, but what is happening is it's actually slightly decreases. Can you think of a reason why? I'll give you a hint over here. Write the electronic configuration. Write the electronic configuration for magnesium atomic number 12 and aluminium atomic number 13, and you will get the answer for yourself. Yes, one is neon. Go on. 3s2. Pause the video. Try it yourself. Give the answer and then check whether it tallies with what I am going to write. Yes, the electronic configuration says it all. In the case of magnesium, you have to remove electrons from the s orbital, whereas in the case of aluminium, you have to remove the electrons from the p orbital. So what is there is, what is more strongly attached to or attracted towards the nucleus, the s or the p orbital? Yes, s is more strongly attached as compared to p. So because you have to remove an electron from the p orbital in the case of aluminium, the ionization enthalpy is actually slightly lower. Moreover, if you see here the electrons, this is s is fully filled. The maximum capacity of the s orbital is 2 and it's full to its capacity, right? So it will have more difficulty because here these two are very thick friends. Whereas in the case of 3p1, it doesn't have company, so it doesn't mind going out and looking for company, correct? So here, so there are, what we have here is electrons being removed from the p orbital as well as the fully filled s orbital. Let's talk about when we were talking about, okay, let's take the case of nitrogen and oxygen. Again, what has been observed is that the ionization enthalpy for oxygen should be higher or lower? Tell me, across the period. Yes, it should be higher than that of nitrogen. But on the contrary, we actually notice that this is not so. Nitrogen and oxygen. Can you explain me this anomaly by writing the electronic configuration? Write the electronic configuration, pause the video, find out the reason, and then let's discuss. Okay, you have the answer for me? I am so glad. Nitrogen 7. What do I write the electronic configuration as? Yes, helium 2s2 2p3. Oh, look at that, the way the electrons are arranged in the p orbital. 1, 2, 3. Hund's rule of maximum multiplicity. Electrons are first singly filled up and then pairing begins. Does that remind you of something? Go on. If you have not, if you can't correlate to this Hund's rule and stability of half filled, request you to go through the topic atomic structure in the series of videos, structure of an atom. Oxygen atomic number 8, helium 2s2 2p4. Yes, see, tell me, 1, 2, 3, 4. What is the reason? Give me just 2 words. Why nitrogen will have a high ionization enthalpy compared to oxygen? Simple. Stability of half-filled orbitals. In the case of nitrogen, the orbitals are half-filled. Half-filled orbitals are extra stable. So you will require more energy in order to remove an electron from here rather than oxygen, because in the case of oxygen, what will happen is it will try to remove that extra electron in order to acquire stability, right? Again, if it is getting too much, just take a short break, take a sip of water, take 5 deep breaths, and get ready for the next periodic property that we are going to talk about. Now, when we were talking about ionization enthalpy, I also spoke about ionization enthalpy first, second ionization enthalpy, third ionization enthalpy. That means when you remove one first electron, remove the second electron, remove the third electron, right? According to you, what should be the trend in the variation of ionization enthalpy 1, 2, 3? Which should be the highest, which should be the lowest? In general, we're not talking about any specific elements. Yes, it is more difficult to remove an electron from a positively charged species than something which is neutral, because positive means now it has an extra proton compared to the electron. It's not that it has gained a proton, but the atom has already lost one electron. Oh my God, it's already undergone a shock. Somebody's taken away its electron. So what is it is going to do? Yes, it's going to get itself prepared so that nobody takes away its second electron. So it's going to pull even stronger. So IE2 will be greater than IE1. Ionization enthalpy 2 is usually greater than ionization enthalpy 1. Same way, ionization enthalpy 3, will it be less or more than IE2? Yes, it will be again greater than IE2. But again, let's go back to our example that we had done, nitrogen and oxygen. Now, if you see the case of oxygen, its IE2 is actually more, it's even much higher than expected than IE1. Can you think of a reason why? Yes, again, wherever you are asked a reason, just go back to the electronic configuration. In the case of oxygen, IE1 means you remove one electron, right? Now it acquires a configuration like nitrogen, half filled, more stability. So IE2, yes, it should be higher, but in this case it becomes exceptionally higher because of its half filled configuration. Let's take the case of nitrogen. Nitrogen atomic number 7, yes, initial configuration, ground state configuration 1, 2, 3. We know that its ionization energy 1 is high, right? If I want to remove one electron from it, I will have to apply a lot of energy. Now, what about IE2? Will it be higher or lower? Yes, it actually gets lower. Why? Because that half-filled stability is gone. Right? This explains some of the anomalies, and also I want to put it across that whenever relating to the periodic table you have any doubts regarding the periodicity, regarding the anomalies, it's best to write the electronic configuration and figure it out as to what is the cause of that anomaly, right? Now let us go on to the next thing that we are going to talk about, and that is the metallic nature. Why I am taking the metallic nature first and not the electron gain enthalpy is because metallic nature is all about losing electrons. We have just now spoken about ionization enthalpy. That means the ability of an atom to lose electron, right? That's the general thing. I'm not sticking to the point to point, word to word definition. It's simply the ability of an atom to lose electron. Metallic nature means it should be capable of losing electrons and forming the positive kernel, right? That's what is a metal. So, when you talk about across the period, what is happening to the ionization enthalpy? It is, yes, it is increasing. So what will happen to the metallic nature across the period? Perfect, it decreases because ionization enthalpy increases, metallic character will decrease. That is why if you notice, sodium, magnesium, metals, aluminium becomes slightly amphoteric, silicon, phosphorus, sulfur, chlorine are non-metallic in nature. On the left hand side of the periodic table you will find metals, on the right hand side you will find non-metals. How is non-metallic character decided? We will do with the further properties. Similarly, when you go down the group, because of the size of the atom is increasing, the ionization enthalpy is, yes, it is decreasing. So down the group, the ionization enthalpy decreases. So what happens to the metallic character? Yes, it will increase. Both are inversely related to one another. Because the atom size is more, it will be easy for me to remove electron from it and for it to show metallic nature. So down the group metallic nature increases, across the period metallic nature decreases. Electron gain enthalpy, also called as electron affinity. So as the name indicates, affinity. What do you mean by affinity? Yes, liking, attraction, right? So electron gain enthalpy. When an electron is gained by an atom, the energy change which takes place is called as electron gain enthalpy. As for now, don't bother about the term enthalpy because you will come across it when you do thermodynamics. In simple, it is also called as electron affinity. How much does an atom want an electron? How easily is it for an atom? Now, what kind of an atom? Yes, neutral gaseous atom. How easily can a neutral gaseous atom acquire an electron is what is measured by electron affinity. Now when you add an electron, that means there is attraction between the positive the protons and the electrons. Because of this attraction, the energy is released. Generally, this electron gain enthalpy can have a positive or a negative value, but I am denoting it as a negative value in order to explain that the addition of an electron to a neutral gaseous atom will be supported only if this electron gain enthalpy is negative. Why electron gain enthalpy is negative? In any system, if energy is released, if energy is given out, it becomes more stable. For example, if I am in a fit of anger, I am like bursting out and I get really angry. After giving a vent out to my anger, I am quiet, calm, more relaxed, more stable. The same thing happens over here. So when it gains the electron, it has to lose energy in order to be stable. So neutral gaseous atom acquires an electron to change into an ion. Now here the ion will be an anion. Unlike ionization enthalpy where a cation was being formed, an ion with a cut, and here it's a negative ion, right? Now here we will notice, now let us see the trends across the period down the group. What kind of an atom will gain electrons easily? A small atom or a big atom? Think. Yes, A small atom. Why? Because that means its shell is closer to the nucleus, and the nucleus says, oh, I can pull the electron, I can pull the electrons towards me. Whereas an atom which is already big means, oh come on, I already have so much of work to do, I can't take in more, right? So let's see the variation of electron gain enthalpy across the period and down the group. I will use the word electron affinity for now, because if I use the word electron gain enthalpy, I will have to talk in terms of the negative and the positive value. So as you move across the period, the size of the atom, again it boils down to atomic size, boss. You just need to understand atomic size. If you understand atomic size, everything is easy. So as you are moving across the period, atomic size is decreasing. So what will happen across the period? Yes, electron affinity increases, or we say electron gain enthalpy becomes more negative. More negative means more energy is being released out. That means more is the stability. That is why if you notice, fluoride, chloride, bromide, iodide, these are the ions that you have been studying about till now, correct? Because all these halogens are easily able to gain electrons because of their high electron gain enthalpy. They have a tendency to gain electrons and form negative ions. Coming to down the group. Oh, yes. There's the noble gases at the end. Why didn't I talk about them when I'm talking about across the period? What do you think will be the electron gain enthalpy of the noble gases? You think they will have a tendency to accept electrons? No, not at all. They are so fully satisfied, they are so fully relaxed, their S and P are all completely filled up, right? If they have to gain an electron, means they have to disturb this configuration. Would they want to disturb this configuration? No, not at all. So, is it easy to add an electron to this peaceful state? No, it's not easy. So, electron gain enthalpy in the case of noble gases, we say it is actually 0, or more appropriately, it is positive. That means it will not release energy. On the other hand, you will have to give it a lot of energy. You'll have to input a lot of energy in order to add electrons to them. That explains why they are not so reactive, whereas the halogens on the other hand are very, very reactive in nature. We are yet to define the variation of electron gain enthalpy down the group. Should I leave it for you to do it and tell me? Okay, pause the video, think and tell me down the group, how will the electron gain enthalpy vary? Electron affinity, will it be strong or will it become less? Go back to atomic radius, think what is happening to the size. You have the periodic table in front of you. Just don't, just sit watching the video. Just think for yourself and then you will enjoy. And that is why when I'll be able to say yes, learning chemistry is fun. Yes, down the group, because the atomic size is increasing, the electron affinity will actually decrease, or electron gain enthalpy will become less negative. That is why if you notice in any particular group, as you are going down, the non-metallic character is actually decreasing. Yes, correct. And that is what we are going to talk about next, and that is what we call as the non-metallic character. Non-metallic character is again based on electron gain enthalpy. How easy it is for an element to gain electrons in order to form the anion, right? Here the negatively charged ion. So the non-metallic character across the period, down the group. Reason it out. Across the period, down the group. It's related to electron affinity. Down the group, non-metallic character will decrease. Across the period, non-metallic character increases. Now you understand why I said in the periodic table, on the left hand side you find metals, alkali metal, alkaline earth metals, group 1, alkali metals, group 2 alkaline earth metals. Whereas on the right side of the periodic table, you have the non-metals, oxygen, fluorine, sulfur, chlorine, bromine, and so on. But in any group, as you go down, the metallic character again begins to show its colors. And what do we have is, in between there's a state where we have elements which show metallic as well as non-metallic character, and we call them as metalloids. Homework for you. What are metalloids? Please list the metalloids. That's a question I am leaving for you to answer. Yes, the video is not yet over. We are yet to discuss the electronegativity. Now, before we go on to electronegativity, now I have talked about atom. So, atom, an atom with a cut, that's a cation. So, more appropriately, a positively charged ion, and an atom with an extra negative charge, ion negative, right? So, now you have to tell me the size order for a cation, an atom, and its respective anion. Think about it. Get the answer ready. It's very, very simple. Again, I hope you are taking down the notes as well. Ion positive, atom, cation. So let's suppose I have A negative, A positive. Can you arrange them in increasing order of their size? Yes. A negative will be bigger than A because it has been formed by the gain of an electron. So if, let's suppose, I take the case of chlorine, atomic number 17. When I am talking about an atom of chlorine, 17 protons are pulling 17 electrons. But when I am talking about A negative, 17 protons are pulling 18 electrons, right? So with the result, the size of the atom will be more. So the size of the anion will be more than the size of the atom. What about the cation? Let me put anion and cation over here so that you don't get confused. Cation, easy to remember. Ion with a cut, positive charge, right? That's a trick told by my chemistry teacher. When talking about cations, here 17 protons will actually pull 16 electrons because it has been formed by loss of electron. So a cation, will it be bigger or smaller than an atom? Yes, it will be smaller. So the size order is cation less than an atom, less than an anion. Of course, there are anomalies. To understand the anomalies, make sure that you just write the electronic configuration. 5 deep breaths. And we are ready to take our next periodic property, that is electronegativity. Electronegativity, again, as the name indicates, it is related to electron, right? What is electronegativity? Now, this is a term which does not come into play when I am talking about an isolated atom. This is a term which comes into play when two atoms are bonded to each other by a single covalent bond. What is electronegativity? Two atoms, chlorine and chlorine, equally strong. Their ionized electron gain enthalpy is equal. They have come together to form a bond and they are sharing it nicely, getting along. Now they are not tugging at the electron pair and they stay that way. So they are equally strong, equally electronegative. On the other hand, if I have a case where one atom is stronger than the other, for example, if I talk about HCl, now chlorine has got high power of pulling this electron pair towards itself because of its small size and also because of its high negative electron gain enthalpy. Just now we've done about electron gain enthalpy. In other words, It releases more energy when electron is added to it. That means it acquires more stability. So when hydrogen and chlorine are bonded to each other by a single covalent bond, chlorine tries to be smart and it pulls the electron pair towards itself. So with the result, what will happen is this HCl molecule, which is otherwise formed by sharing of an electron pair, behaves like a partial ionic compound. So what happens is chlorine acquires slight negative charge and hydrogen acquires slight positive charge. Mind you, they have not been formed by losing or gaining electrons. What has happened is initially they started as very good friends. Okay, let's go and buy let's say a cotton candy and we'll share it. Yeah, very good. We are very good friends. And then chlorine, being more powerful of the two, takes away the major share of the cotton candy, right? And hydrogen cannot say anything. So with the result, this is slightly positive, this is slightly negative, and these are what are called as polar compounds. On the other hand, a molecule like chlorine, Cl2, where both of them are equally powerful and it behaves like a neutral molecule, are called as non-polar compounds. So what about electronegativity across the period, down the group? Think and tell me. ATP, DTG. Again, yes, simple. Size of the atom. If you talk about the size of the atom, what is happening to the size of the atom across the period? Decreasing. What is happening to the electron gain enthalpy across the period? Increasing. So what is happening to the electronegativity across the period? Increasing. Yes, down the group. Give yourself a pat or show me that smile if you really got it right. Down the group. Atomic sizes increasing, electron gain enthalpy decreasing, electronegativity decreasing, right? Oh yes, I forgot to tell you, arrow up means increase, arrow down means decrease. Please write the full word decrease and increase when you are writing in the exams or in your notebooks. These are just simple ways of making notes, taking down notes and doing it a bit fast. So a little into the habit of it, and I find it much more interesting to write it this way. So we have talked about electronegativity as well. Now here I'm going to talk about a little about oxidation potential as well. For defining the oxidation potential, I want you to tell me what do we mean by oxidation first of all. Can you recall about oxidation in terms of the number of electrons? Yes. Oxidation in terms of electrons. O for oxidation, loss of electrons is oxidation, right? So if an atom loses electrons, it is getting oxidized, right? So sodium, when it loses an electron, it forms Na positive and an electron is lost, so it's got oxidized. If an element has a tendency to lose electrons easily, will it help in other atom to lose electrons? It itself is losing electrons. So sodium has a tendency to itself lose electrons. So let us suppose another atom comes to it, magnesium, and says, help me to lose electrons, please take some electrons from me. Will sodium help it? No, sodium is itself looking for opportunity to lose electrons. So sodium does not help magnesium to lose electrons. In other words, sodium does not act as a good oxidizing agent. It is itself losing electrons. On the other hand, let's say chlorine. Magnesium goes to chlorine. Magnesium says, I have 2 electrons extra. Can you help me? Chlorine says, why not? I will call another friend of mine and we can take away the electron from you. So chlorine gains that electron. Of course, in that gain, chlorine has got reduced. Right? Let me make the board a bit more clearer for you. Yes. So this sodium changing to Na positive is oxidation, loss of electron. Gain of electron is reduction. How will it gain electron? Only when some other element gives it electron, right? So if sodium is losing electron and chlorine on the other hand is gaining electron, they are mutually helping each other, and as a result they will become friends, right? Now coming to what I want to tell you over here. Now chlorine, because it has a tendency to gain electrons, that means itself it is getting reduced, it is a good oxidizing agent, right? Because it is helping the other atom to lose electrons, correct? A good oxidizing agent gets reduced. On the other hand, sodium is giving electrons to chlorine. So in other words, sodium is acting as a reducing agent. Does that make it clear? Oxidation is loss of electrons, reduction is gain of electrons. If something is getting reduced, that means it is acting as an oxidizing agent. So when you see across the period, what is happening is the size of the atom is decreasing. Electron gain enthalpy is increasing. That means across the period they act as very good at the oxidation potential, or the ability to act as oxidizing agents increases. So oxidation potential, yes, increases across the period, right? And that is why we find that fluorine is the best oxidizing agent, because down the group again oxidizing power or ability to oxidize the other atom will again decrease. So what do we find over here is that fluorine, it matches the best criteria. It is at the end of the period and the top of the group, hence the best oxidizing agent, right? One last heading, so just take 5 deep breaths and we will talk about diagonal relationship. Diagonal relationship, as the name indicates. Now here there is a special anomaly which is seen in the case of period 2 and 3. You are saying that across the period something is increasing and down the group it is decreasing. So increases, decreases, increases, decreases. Now, or we talk about a property, let's say we are talking about atomic radius only, right? Across the period it is decreasing, down the group it is increasing. So here's an increase, here's a decrease and here's an increase. So when you are going like this, it is increasing, and when you are going horizontal, it is decreasing. With a result, what will happen is diagonally, if you see the effect, it nullifies. The increase nullifies the decrease. With a result, we find that in a number of properties, the elements in the second period diagonally resemble the elements in the third period. So lithium, magnesium, beryllium, aluminium, boron, silicon, carbon, phosphorus, nitrogen, sulfur, oxygen, chlorine, right? So in a lot of properties, physical and chemical, the elements of the second period diagonally resemble the elements of the third period. This is what we call as diagonal relationship, and this can be attributed to a decrease in atomic size across the period and an increase in atomic size down the group, which cancels the effect of the increase and the decrease, making them their atomic sizes similar, and hence their behavior also is quite similar. I hope you've understood periodic properties. I've made my best attempt at doing so. In case there are anomalies, please get in touch with me, and I shall be happy if you can subscribe for more videos and share it with family and friends so that they can enjoy learning chemistry in an